Good evening, everyone. Thank you, Nishant, for setting that up. No pressure now. So my name is Amit Kapoor. I kind of work in the intersection of data, visuals, and stories. And my background is in management consulting. And kind of like that's where I kind of come from in terms of telling stories with data. So how do you tell stories that make change happen? And to a large extent was very data-driven. So I'm going to kick off this session visualizing ML models or machine learning models. And the idea here is basically to kind of talk about some of the thoughts I have. So I'm mostly into data visualization and data science. And I wanted to kind of explore how we could bring a lot more of the visualization capabilities that we have onto the modeling side also, right? So that's the intent. And what I'm trying to do here is basically have a conversation with people around how to think about this, how we can build on this, because the tools and the ways to think about this are still far more nascent than maybe data visualization is. That's the intent. So this is the last session. There's no one after this. So we can keep it interactive. If you have any questions, just feel free to stop me in middle, ask a question, and we'll try and make it a little more interactive rather than just me talking, which me being on stage already feels like a little bit like that. So is that okay? Yeah? Yeah? Okay. So let's start with a story. So we don't see things as they are. We see them as we are. So let me talk about a story. And how many of you have heard of the story of the blind man and the elephant? Okay, a fair bit. Not all, surprisingly. So the story is very simple. It's basically six blind men who had never seen an elephant before, were very curious about seeing an elephant, were brought to an elephant. And when they was brought to the elephant, the first man actually approached the side of an elephant and felt it like a sturdy and pretty much very strong and said, this is definitely a wall. So an elephant is like a wall. The second man went and touched the tusks, which was very smooth and very sharp, and said, this is definitely like a spear. The third one actually fell to the ground and happened to catch the knee of the elephant. And touching it, realized, well, this is definitely like a branch. The fourth one was stuck by the trunk. And holding the trunk and seeing the rigid trunk and its smooth tongue said, this probably looks like a branch. The fifth one caught the ear. And the ear was flapping, was large, and said, this is definitely like a fan. And by the time the sixth one came, the elephant had turned around and was stuck by his tail and felt that whip and said, this is definitely like a rope. So the blind man and the elephant. And so these men of Hindustan disputed loud and long, each in his own opinion, exceeding stiff and strong, though each was partly in the right. They were all in the wrong. So why do I start with this? What's the elephant for us in this case? The elephant is really the data. And as I like to say, the data is just a clue to the end truth. We're trying to look at the world in this data-driven lens. And what we need to realize is not the moment the data hits us, it doesn't become the objective truth. It's still a clue to the truth. And we're trying to understand a phenomena behind what the data is trying to tell us, right? And we, the men, are trying to build a model on it, right? And as George Box said, maybe in the 70s, I think, that all models are wrong, but some models are useful, right? So the intention of us is not to build a perfect model, but is to build a model that is useful for us to understand the phenomena that's happening. How does that link together? How do we link this kind of data as a clue, and how do we link it to this building a model, right? I kind of think of layers of abstraction. So everything is a layers of abstraction that we're trying to understand, right? And when we look at this, we kind of think of 3 layers of abstraction. There is a data abstraction, so how the data is, what the data is trying to tell us. A visual abstraction, right? And a model abstraction, or if you want to say a symbolic abstraction. And we all operate between these 3 layers of abstraction when we're trying to do data science. If that layers of abstraction seem pretty different to understand, we can translate this into more machine learning speak. So the first step, or one of the steps, once you've framed the problem, you've acquired the data, you've refined it, you probably be between these 3 layers of abstraction. Transforming the data, so transforming the data from one form to another, because just because it's measured in one way doesn't mean it is applicable to the other way. Visual exploration, and model building, right? And this 3 is the crux of any machine learning or data science process, right? And once we've done that, we probably have something to communicate. So you acquire, refine, frame the problem, acquire the data, refine it, and then you move between the cycle of transformation, exploration, and modeling in a very iterative fashion, right? Does that make sense? Does that feel like what we all do? So if you think of the machine learning pipeline, we all are familiar with kind of data transformations and the concept of tidy data. Anybody who's come from probably is aware of Hadley Wickham or uses R, and the concept of tidy data is that every data is in observations. Observations are in rows and every variable is in a column, and that kind of tidy, at least in a tabular data sense, is what is the concept of a tidy data. And on the tidy data, we do visual exploration, which is data-vis, which is what I kind of focus on. But if you see, there is also a link that goes from data transformation to model building. So we take the data and we transform it, but we don't close this loop, or we rarely close this loop. I have a friend who's a data scientist, pretty successful one at that, and he rarely uses visualizations to even do visual exploration to a little extent, or to do any model exploration, right? So this skill about doing any visual exploration on the model is really very, very hidden, if at all, right? So most of them would be very comfortable doing numerical summaries to understand what the model is, how it feels, but not really think, how can we understand this model in a visual way, right? And there is some benefit to that, because modeling does scale very well. Modeling is really fine because modeling scales nicely with data. Visualization doesn't scale that nicely with data, so it is not that easy to think about it. Visualization is important because it helps us understand what I call the second level of ignorance, right? So first level of ignorance is I know what I don't know. The second level of ignorance is I don't know what I don't know. And if I want to really understand or get a sense of my blind spot or what I don't know what I don't know, I need to visually explore it, right? So we need to kind of close this loop. And so an extended ML pipeline would probably have these 2 components also into it. So you have tidy data, you have data-vis, but we need to have something called like a tidy model. A model that is tidy in its nature that we can actually do model-vis or model exploration on that, right? And once we do that, we kind of have a parallel to what we are doing in data transformation, and we can use visualization as both this connection to do it, right? That is the whole idea of actually doing model visualization, right? How can we connect these 2? So how do we do this, right? Any thoughts? Does anybody do this? How many of you use do visual model exploration? None? A few hands?
Model and you see how it's faring.
Correct. So that would be one component of that model. So seeing the errors in that context. What else? What else has somebody done? Yes?
It could be lift chart.
A lift chart in promotion. How much is the lift? Okay. Yeah, that's fine. I heard him. Anything else? So my hypothesis is that all of you do it in some way or fashion, but probably don't have a way to name what you're doing, right? And one of the things I guess I try to do is basically structure things because I also teach this stuff, right? So this helps me formulate my understanding and also helps me to explain stuff, right? So I kind of think of model-vis as kind of these 8 buckets. They start from 0, so they're actually 7. But before you can do model visualization, you probably need to do data visualization, right? So you visualize the data space. You visualize the data space and then you visualize the predictions in the data space as much as possible in the data space, right? Once you've done that, you visualize the errors in the model fitting. That is what the lady out there just mentioned in forecasting. She was trying to measure the errors in the model fitting. Then you also want to visualize not only that model error in the model fitting, you want to visualize how the model looks with different parameters, right? So how does that behave with different parameters? So visualize with different model parameters and visualize with different input data set. Because what you have right now is just a sample of the data set, right? So you want to also visualize it with different input data sets. And you want to then not only build one model, hopefully, you want to build many models. So you want to visualize the entire model space. Having done this, maybe for some feature selection, you may actually want to do it for the entire feature selection or dimensions that you have, so the entire feature space. And in many cases, you won't be building just one model, you'll be building many, many models of different kind on the data itself. So not that one data model, but multiple models to understand. So simple way like the forecasting example, if you want to forecast at a store level, for each product, there are probably different products. You're probably building 1,000 models or 10,000 models. So there are many more models that you build, right? So these are the steps that go into model-vis, right? And does that make sense? Yes.
Output, parameters, or what?
Yeah, so visualize with different, okay. So you probably, once you've gone from the data space to the prediction space, mostly you're either doing prediction or error visualizations. So you're probably trying to understand the predictions. What does the prediction look like when I tweak the model?
So that's like doing step 1 and 2 with a variation of 3 and 4.
Step 1 and 2 with the variation of 3 and 4. Yes. Well, kind of. Let's take an example, right? Let's take a simple example. So I'm going to take 2 examples over the course of this talk. One is just a simple regression example, 50 data points, about 4 variables. And then a second, slightly bigger example on classification, where at least 2 classes, about 5K of data, and about 785 features. Okay, so slightly bigger in both directions, right? And again, this is really thoughts that I have. They're not, they're just a way to have a conversation on this, right? So let's take the regression. The biggest thing in India, if you're going out to go buy a car, is, what's the biggest thing in India? Kitna deta hai, right? What's the mileage? What's the mileage for the price that I'm willing to pay, right? So there is a cars data set which I scraped from a car comparison website. Its price versus KMPL, I refined it, I tidied it up. And then there's obviously is a huge database, or not huge really, but like 800 cars across about, I think 60 features. But for this purpose, I'm just using base version for every petrol car, so I'm not looking at trims. So basically remove the trims, only looking at petrol cars. And I'm looking at under about 10 lakhs. So we have about 42 cars to look at, right? So let's go through each of those 7 points and see how they look like, right? So this is how the data looks like. We have brands, and this is in the ascending order of price. So a Tata Nano at the bottom at about 199, which is 1,000, so it's about 2 lakhs. At 23.9 kmpl, a hatchback with 38 horsepower, and a Volkswagen Vento at about 7.85 lakhs, 16 kilometers per liter, a sedan at about 104 horsepower, right? So that's kind of the structure of the data set. We'll start with just the basic 2, price versus KMPL, because that's really what we focus on, right? So let's see if we can talk through each of the data set, right? So what is visualize the data space? In this case, it's pretty simple. We have got about 42 points, not really too many. We can plot all of them. And we have basically 200 2 lakhs to about 8 lakhs on the top, 14 kilometers per liter to about 24. That's kind of the data set, and these are all our 42 points right now that's there, right? So we kind of visualize the data space. What do you visualize next? You visualize the predictions in the data space, right? Now, once I do this, you'll realize many of you do pretty much all of these steps, right? But you haven't thought about how to articulate this for each and every case, right? So we now have a prediction space, and I can draw a line, but for this moment, I've just drawn an example of a regression line. And for a moment, let's say this is an ordinary least square line, okay? It could also be a ridge regression line at alpha equal to 0, but both of them are same. So let's say right now it's OLS for 0, right? We visualize the errors in the model fitting, and in this case, I have not balanced them at 0, but we can look at the differences between each one of them. And once we visualize the errors in the model fitting, we probably want to visualize how the model looks like with different model parameters, right? So this process of actually now, if we were to change that line from an ordinary least square to a ridge regression, and we keep changing the alpha, L2 regularization for those who are following up, L2 regularization, we're changing the alpha, and we're basically going from alpha equal to 0 to about alpha equal to 1. And as you can see, the line gets constrained, right? So this is now we are visualizing with different model parameters. Still one model, but now we're playing around with different model parameters. What is visualizing with different data input set? I basically take the same data, and I sample it, and I sample it, and I sample it, and I construct different lines for sample of the data. So say, let's say about 20 samples from 42, and for those different samples, I'm basically trying to create more data out of the 42 that I have, right? A process not unknown to many of you, probably called Bootstrap, but I'm trying to generate more data because I only have 42 models to do that, right? 42 data points to do that, yes.
Are you going to generate extra data from the same sample set?
Yeah, so if I sample with
You're generating the extra data set based on data that exists.
right, so bootstrapping, or suppose I only have limited data set, right? So I have 42 data points, but I want to check whether my model is correct. I take, say, 20 of those data points, and I fit a line, right? I take another 20 data points, now with replacement. That means I can actually select the same car twice also, but with replacement, I generate another line. I keep doing this for about 1,000 lines, 100 lines, as many as you want. And what I'm trying to do is basically to prevent overfitting, right? So this concept of bootstrapping is one way of trying to prevent this from overfitting, which is pretty common, right? So as you can see, this is a ridge regression. So I'm keeping an alpha, and I'm playing with the alpha also. But I'm trying to, I get a different line every time. And if I play with the alpha, actually in this case I'm not shown it, you can actually see how this thing goes out. So if it is an OLS, the variance would be very high. The bias would be pretty much the same. With ridge regression, the variance will go down. The bias will go up a little bit. But we don't need to get into the math of it. The bias doesn't go up that much, but the variance really shrinks. And that's why you do ridge regression as a way of regularization. And that's one of the techniques. The other way to do this would have been probably to play around with errors and try and do some kind of cross-validation, right? And then try to get something, again, of a more constant line, right? Does that make sense? Yeah? So the concept bootstrapping is pretty common. Like when you do a random forest, you're trying to do something like that. You're taking trees, creating trees, and you're doing bootstrapping in a different way at tree levels and what branch to choose, but the idea is the same, kind of. A very common technique, right, to do this. So I'm visualizing now with different data input sets. Then, I'm actually now so far only working on ridge regression, but actually I can have an OLS, I can have a ridge regression, I can add a LOS to it, I can add a polynomial tree to it. So I'm going to make many models. And eventually, I may actually end up choosing to add them up in what is the darker blue line here, which is something like an ensemble model, right? So I'm basically doing ensembling. I'm looking at the entire model space, whatever the possible models that I could fit, and then I'm trying to combine them, in this case in a very simple weighted average fashion, but I'm basically in sampling, right? So I'm trying to visualize the entire model space. That's step 5. So far I was just at price, NK, MPL, but I have 2 other features. In this case, I have what is a sedan and what is a hatchback. So the hatchbacks are obviously the cheaper ones with more mileage. The sedans are on the top. And you can already see that there seems to be a different pattern with them. And also, I have horsepower, BHP, which in this case, because I have a 4th variable, I can represent by size. So the size of the circle represents BHP. The smaller ones are on the bottom. The bigger ones are on the top, right? And now I have 4 data points. And now I can fit actually, now this is the entire feature space. And to play with this, I can actually fit a single model, which I've been doing, or actually split these 2 into 2 separate models and start to fit multiple models, which is the concept of fitting n models, right, or many models in this case. And so in this case, suppose I want to fit a low-S model. So the red empty circles are what I fitted now as a prediction space using a low-S model, and the blue empty spaces, the blue circles with nothing in the middle is what is the prediction for the hatchbacks. So obviously getting much closer, the errors are going down. And I can build cross-validation on it, and I can continue this process, right? So I visualize the many models together. Now this is, even though there are only 2, you can extend this concept to pretty much any extent, right? So this steps 0 to 7 kind of combines together to be kind of the model-based approach. And you don't do all of them all the time. You may pick and choose depending on what your strategy is. You may be focusing on bootstrapping, you may be doing on modeling. But in essence, you need to know how to do this for each one of your data sets or any type of domain that you're trying to do. And this is a simple regression, much more easier to explain. But each of this have a direct correspondence in ML or machine learning, right? The data space, what we're trying to do is data-vis. Prediction in the data space is just predictors or predictions. The error in model fitting when we try to do is basically cross-validation or validation. Cross-validation is one technique of validation. When we do with different model parameters, that's what you call tuning a model. With different input data sets is bootstrapping. When you kind of combine the entire model space or play with the many models together, you are probably playing with some kind of ensemble technique, so ensembling. The entire feature space, or trying to evaluate the feature space, is basically feature engineering or feature selection or feature creation, some part of that. And the last one is probably not that popular as a name, but it's probably something many of you do definitely in sales and marketing kind of jobs, which is N models, right? So how do you bring the N models together, the many models together? So these 7 steps kind of have, or 0 to 7, have direct congruence with everything we do mostly we do in machine learning, whether it's model building, model validation, or model testing, right? And they all kind of trap into it. And the hard part is trying to extend this to many more ideas, right? So if you think about it, there are very limited standard methods that are articulated. If I was to talk about data-vis, I can probably go on for a couple of hours and talk about how to go from 1 dimension to 2 dimensions to 3 dimensions to 10 dimensions in a statistical data point and have very well-grounded techniques on how to build this up. If I was to talk about model-vis and I just change any other model space or data type or domain, it's really hard to talk about, right? So you need to really adapt to data and domain, and it's really interesting because I think there's a lot of opportunity to try to combine a lot that is happening in the machine learning world with the visualization world to do something interesting. That's where my interest lies, and that's why I'm trying to think about these topics, right? Calamari? So, what is the idea? Why are we trying to do this? The key concept here is, even though modeling scales really nicely, and to a large extent machine learning is built on the idea that I'm going to learn from the data, there is still a lot of intuitive knowledge that I have, the implicit knowledge I have about the domain. So the idea of model-vis is to help me find the implicit knowledge I have and try to bring it explicitly into the model, right? It's just that process that it needs to really facilitate. And whether you use some of these techniques or part of these techniques doesn't really matter. As long as that loop is getting closed in terms of your implicit knowledge about the data, or maybe even your blind spots, what you don't know, coming out and then helping you bring that implicit knowledge into the model, that really is powerful. Because we're still talking about human in the loop. If there was no human in the loop, we would probably have automated pretty much everything. And yes, there are domains where you can do it, maybe image recognition and neural networks you can do probably around. But there's still a lot of places where people are trying to understand how the neural network works in a model or in visualization, right? So I'm going to take this forward a bit. And I'm just going to talk quickly through one more example. I'm going to take a very standard toy, not the standard, but the standard machine learning example that everybody uses when they do any new neural network, tested on the MNIST data. But we're going to simplify it a bit, right? So MNIST is basically digit recognition, 0 to 9, if somebody is not familiar with the data set. And we're going to reduce it to two classes. So we're going to reduce it to two classes, which is just 1 and 2. So we're just trying to figure out between number 1 and number 2, which is handwritten, right? And the data set is basically one parameter which says what the label is, which is 1 or 2, and a set of features, which is 784, which ultimately can be mapped into a 28 by 28 pixel gray map, right? And for this 1 and 2, we have about 5,000 data points, or more than 5,000. How does that look like? So that's how the MNIST looks like if you kind of plot it with each segment, 28, and you can look at each pixel is a gray point, and if you interpolate, and you can actually see the pixels in this case because the pixels are really grown up. So there on the left is a 1, second on the right is 2, right? And how do we can look at this, and if you want to visualize the whole data space, we can just actually just do it on this, right? So, and that's why every domain would have its own way of trying to map the data, right? Onto how, or every problem would have its own way of mapping. So we can map all the data of 1s onto there, and all the data of 2 onto that space. That's one way to represent it. But probably not the best way for us to go forward and try and do something with it, right? So one of the things we can do is, okay, obviously we can see that there is some level of symmetry around it. And we can basically use symmetry and intensity as two ways to kind of pick this up, right? We can basically say 1 is more symmetric, the 2 is less symmetric. So we can use symmetry as one character, and 1 is obviously much less brighter than 2 if we aggregate it, so intensity is an aggregate factor. So we can basically take intensity and symmetry as the 2 dimensions and plot it, right? And we can already start to see that in this reduced feature space, I can start to separate the two of them. I can add the predictions in the data space. In this case, I'm plotting probabilities. Obviously, the stuff in the middle is something that you can't really see. It basically is a vertex color map. So going down, and the stuff in the middle is what is less probability. And if you were to just plot the errors on top of it, you'll find that the errors are basically around that center part, which probably makes sense because I'm using a very simple classification method to do it, which is basically a logistic regression, and I can build the prediction boundaries there. I can create a mesh, so I can create a mesh of all the possible points are there, and I find I use the algorithm on it, I can actually see how the prediction boundaries look like. And I can actually do kind of what I did earlier. I can start to look at model parameters on this, and this is now logistic regression with C, a cost function changing on this, right? And we can keep to do the same thing on this, right? We can extend this much more. I will do that. But the real challenge is really in model-vis is what happens when the n is large and we have big data. What happens when p is large, or we have high dimensional data, or when we have large number of multiple models. In all these cases, it really becomes much more harder to do this, right? So in our case, how do we scale p? What do we do when the p is really large? So we have kind of what I would call the cursor dimensionality. We can't really visualize more than 2, 3, or maybe 4, 5 dimensions. And to do the mesh approach that I'm doing doesn't really scale very well computationally, because the moment you have lots of features, it'll start to break down. So you need to start to go and use some kind of projections. And you can, for the entire feature space, create a TSNE projection in this case. And once you have the TSNE projections, and you can clearly see the 1s and the 2s are separating out in this TSNE projections, you can start to do the error modeling on top of that and see how the errors are placed out. Now, you can even extend this further and start to see how the trace data plots on this and actually use this method to get back the dimensional or the boundaries of this. It's a little more harder to do it, and the tools are not there really for there. There are a little bit of experimental Python programs right now. People are trying to do this visually. But you could extend this method, or not maybe TSNE, but any other kind of dimensionality reduction, PC or all, to basically bring back the boundaries and start to visually see. The idea being, again, to build the intuition about the model and translate that, right? So you may even actually do it on a sample of the data set. Okay, so I'm going to stop here, or I'm going to just wrap up quickly. So N model approach, what do you do for N? If you have a large N from a database, you largely do binning or sampling. Binning is the most powerful method because binning or creating generalized histogram is how you can actually overcome a lot of the N problems, so large number of observations. You have to use projections. Mesh doesn't really work that well. Tours don't really work that well, but some kind of high dimensionality reduction would probably be an effective way to start to look at clustering. And for N, you really need to use summaries. Okay. Okay. In practice, doing this is really hard because you start to hit a lot of model explosion issues, right? So you suddenly have so many models that you need to keep track of. And the tooling, so you need to keep track of the predictions, the errors, and how the parameters for each of those models that you're building in. And the tooling to do this is really something that you need to build around tidy models. So a way to augment your data frame with predictions, errors, output parameters, kind of like create the same data tidy that you have called data model. And there's a little bit in R now these days, just recently launched in data-vis, basically Broom and Purr, which try to help you do it. Python has a PyBroom package and a little bit of experimental package to do it. But the tooling in Python is largely roll your own kind of thing right now at this moment. I'm just going to end here. So similar challenges to data-vis, more an art than a science. I believe, and maybe this is my bias, an integral part of the data science pipeline that everybody should build their capability on and go further than this. And it can be used both for explaining and predicting. And given that it's an open space, anybody who wants to develop more tools on this should look forward to. I'm going to write much more on than this, what I've covered in the talk, in basically model-vis.amitcaps.com. If you go there, right now there's just a TOC, table of content, but you'll get a sense of what will come out there. And most of the code I write is on GitHub, so there's a model-vis repo on GitHub, which has some of the earlier talks I've given and all the code that will come out of this. This should come in the next month or so. And I'm happy to